surprise to Eno. During work on an earlier Eno album, Another Green World, the Cards reduced Phil Collins, the superstar drummer from Genesis, to hurling beer cans across the studio in frustration. Faced with Eno's random chord experiment, Carlos Alomar complained that this experiment is stupid. The violinist Simon House commented that the sessions often sounded terrible. Carlos did have a problem, simply because he's very gifted and professional. He can't bring himself to play stuff that sounds like crap. Yet the strange, chaotic working process produced two of the decade's most critically acclaimed albums, Low and Heroes, along with Iggy Pop's most respected work, The Idiot and Lust for Life, which Bowie co-wrote, and which benefited from the same messy approach. Low was arguably the bravest reinvention in pop history. Imagine Taylor Swift releasing an album full of long, pensive instrumentals, and you get a sense of the shock. It's hard to argue with such results, and Brian Eno's oblique strategies now have a cult following in creative circles. The Berlin trilogy of albums ends with Bowie's Lodger, a record with a revealing working title. It was originally called Planned Accidents. Given both Jarrett's and Bowie's experience, it seems that arbitrary shocks to a project can have a wonderful, almost magical effect. But why is that? One might expect the answer to lie in our psychological response to these curveballs, but that is only partly true. The advantage of random disturbances can also be seen in a far more technical realm, mathematics, full of practical applications. Take the question of how to lay out a circuit on a silicon chip. Starting with a description of what the circuit should do tells us which parts of which components should be wired to other components. But there are trillions upon trillions of conceivable ways to lay out the wiring and the digital logic gates that make up the circuit, and some are much more efficient than others, making a big difference to the performance of the chip. This is an example of what mathematicians call an NP-hard problem. NP-hard problems are a bit like enormous combination locks. If you're given a solution, it's easy to check if it works, but it would take an impossibly long time to find the solution yourself by systematically trying every combination. Fortunately, the silicon chip problem differs from that of a combination lock in one important way. With a lock, only one solution will work. With a chip, manufacturers don't need to find the ultimate circuit layout, they just need to find one that's good enough. To do that, they use an algorithm, which is a recipe for a computer to work through different possibilities. A good algorithm will get you a decent solution without taking forever. But what makes for a good algorithm? One recipe that won't get very far is a systematic check of every possible layout. That's hopeless, because it might take a lifetime to stumble across a good answer. Another is to start with a random layout and look for incremental improvements, a small change that makes the layout work better, for example, moving just a single component and redrawing the wiring to fit. Find another small improvement, then another, then another. Unfortunately, this method is likely to send you down a dead end. A point will come where no single change can make the circuit more efficient, even though several changes at once, perhaps moving several components together into a cluster, would produce a big improvement. The better method is to emulate Brian Eno and introduce a judicious dose of randomness. For example, an algorithm called simulated annealing starts with an almost random search, willing to try any change, good or bad. Slowly it becomes fussier about what changes it will accept, until eventually it has turned into a rigid search for small, step-by-step improvements. There's no guarantee of finding the very best circuit layout, but this kind of approach will usually find a good one. The combination of gradual improvements and random